Hello, this is Unlock Circuits 18EC42, Module 3, Lecture 1, Part 6. We are discussing about the feedback amplifiers in the Part 1 to Part 5. We discussed about the basic feedback structure and then the 4 different types in brief, and then the first 3 types, which is series shunt, series, and shunt type of feedback topologies. This is Part 6, in which we will be discussing about the shunt series feedback topologies. I am Dr. Noorullah Sharif, Professor and HOD, CCAB Institute of Engineering and Technology, Vijayawada. So the shunt series will be straight away corresponding to the input is in the form of shunt and the output is in the form of series. So output is basically here, because it is series, it is the current which is I0, and because it is shunt at the input, it is again the current mixing which is happening at the input side. So current mixing we have here and current sampling we have here. So the feedback value will be IF is equal to beta I0. So beta will be equal to IF by, IF is equal to beta into I0. So beta will be IF by I0. Similarly, the basic amplification here, A will be equal to this is a current amplifier. So therefore it will be I0 by II. I0 by II. So you can see that we have here IS. IS is the current which is flowing into this, and II will be the one which is entering here, and IF will be the one which is coming here. So therefore IS will be equal to II plus IF, or II will be equal to IS minus IF, either way. Okay. So the same thing is being mentioned over here. So we are just not considering the RS and RL. We are not considering the RS and RL, and we are writing here a current source which is dependent upon the input current. Current source which is dependent upon the input current. And the R0 over here. So here in the feedback, we just have the beta I0 value, which is equal to IF. Okay, again, the value of IS is equal to II plus IF over here. So RIF is measured here, ROF is measured here, and then we have all the input resistance, current gain, and R0 output resistance. So the beta is a ideal current sampling shunt mixing feedback network. Source and load resistance are included inside the amplifier. We are not considering outside, and we are considering that they're part of A, and A is nothing but I0 by II. A is nothing but output current divided by the input current, because it's a current amplifier which we are talking about. So now this is the feedback equivalent circuit with feedback, which is there here. That means we are trying to replace the overall feedback, amplifier with the feedback circuit together is RIF here and AFIS and ROF over here. So AF is equal to I0 by IS. IS can be considered as again II plus IF. IF can be again written as IF can always be written from here as beta into I0, and the same thing can be substituted there, and we will get the the common terms we can just take out, and at the end we'll get this result. The input resistance RIF will be here. If you go back, if you RIF is this value, which is equal to the value VI by the value which is IS. RIF is nothing but VI by IS. But however, the value of the VI, the value of VI can also be written over here, VI as II into RI. So same thing is written over here. VI is equal to IIRI divided by IS. IS can be written as again II plus IF, and then IF can be replaced by beta I0, and then I0 can be replaced by A into II because of the current amplifier which we are having in the earlier circuit over here, because of this circuit. Then II common you can take out, II will cancel, we are left with Ri by 1 plus A beta. So we are having shunt mixing at the input side, and that reduces the current mixing, you can say, or shunt mixing, you can say, which reduces the input resistance by 1 plus A beta. The general form for the impedance, this is resistance, and if we consider impedance, then it will be ZIFS is equal to ZI divided by 1 plus A into beta. Then the output resistance is to be measured. For that, what we do, on the output side, we put a test current source and we make the input source current equal to 0. So at that time, we will have this type of equivalent circuit where ROF can be considered as V by IT, where V is the voltage across the, what you call, this network over here. So in this case, II is equal to minus, what you call, II is equal to IS minus IF. IS is considered 0. So therefore, it is just minus IF. IF can be replaced by beta I naught. I naught now presently is the test current itself, which is IT. So therefore, it will be minus beta IT. So we are considering IS equal to 0. Because of this, we are going to get this. So now, this value of, you know, the V value here is the voltage across the R naught, and voltage across R naught can be considered as, you know, the current flowing through this, and the current flowing through this is, this current is going like this, and part of it is going out here. So the current over here will be II minus A, what you call, IT minus A II, and that multiplied by R naught is going to give us the value of the voltage over here. So V is equal to IT minus AII, that is the current flowing through R naught multiplied by R naught. Then the II itself can be replaced by minus beta IT, and that's why we are going to get here plus A beta IT. IT you can take out common, V by IT will give us the ROF, and that is R naught multiplied by 1 plus A beta. So the current sampling feedback increases the output resistance by 1 plus A beta, and that is why we are having this, you know, generalized equation as ZOF is equal to ZOF is equal to Z naught multiplied by 1 plus A beta. So that is the ideal case, because we didn't bother about the RS and the RL. Now we are considering RS, RL, and also we are replacing the feedback network with a more accurate model. So we are just trying to write a practical case over here for the shunt series feedback amplifier, and you can see that the RIF is this one, which is RS plus RS in parallel with RIN, and that is 1 by RIF is equal to 1 by RS plus 1 by RIN. So 1 by RIN will be 1 by RIF minus 1 by RS. So therefore, RIN will be inverse of whatever is there on the right-hand side. So that's what we are having here. That's what we are having here. Similarly, the R out is equal to ROF minus RL. ROF is considered to be, you know, somewhere, here. That is the value which we will consider here. So that is the value of, really speaking, we consider that this value is nothing but the R out, and hence, because they're coming in series, R out plus RL will be considered as the value which is ROF. R out is considered somewhere here in series with RL. So ROF is R out plus RL, therefore R out will be ROF minus RL. Now that is what we are trying to do over here. RS, we are writing RS also, we are including RL also over here, and then we are taking the ROF here. So that means RL and ROF are going to come in what you call somewhere. Really speaking, it is not this. It might be somewhere here, right? Somewhere here. and they are coming in series, and that corresponds to the the RO. Our out is going to come somewhere here, and ROF will be the summation of those two. The source, now this is a network. Now this is can be considered as a inversion of the hybrid model. Okay, can be considered as an inversion of hybrid model. Let us not bother about the what you call mm, so to say the dimensions of G11, G12, G21, and G22. Let us just consider that on the output side we are writing a Thevenin model. On the input side we are considering a Norton model. Now this value is G11 can be again lumped at the basic amplifier side, and this G22 also can be modeled at the what you call output side, and they can be considered as resistances. They can be considered as resistances. This does not have any unit because this is a current source and you are multiplying with current. Now this G21 has G21 V1 again. G21 is not having any what you call unit because this is a voltage source. We are multiplying it by voltage. Okay, generally we neglect G21, and this resistor are lumped onto the two sides there. So only this we will consider in the next figure. So we are lumping G11 here and G22 here, and G21 is neglected. G12 is what is considered here. So the value of beta equal to G12 will be equal to I1 by I2 when V1 is equal to 0. So this just gives you in the similar way the summary of the shunt series feedback amplifier with feedback, and in the A circuit to find the value of A, we are using this type of circuit where we are lumping with RS the R11, and similarly the R22 we are lumping at the what you call output side. Then the value of R11, how do we find, and R22, how do we find, which is same thing as G11 and G22 in the earlier circuit, and the gain A will be I0 dash by II dash. Then the way to find beta will be this circuit over here, where we are just trying to short the input side and correct a current source at the output side. Then we'll get beta is equal to IF dash by I0 dash when V1 is equal to 0. So let us stop at this for the what you call theory part. We'll take up the numerical.